Have you ever stopped and wondered if there's like a hidden language that describes the entire universe? A secret set of rules that governs everything from the path of a planet to the ripple in a pond? Well, turns out there is. And today, we're going to learn its basic grammar.
I mean, really think about it for a second. All of these things are moving, right? They're constantly changing. A planet's orbit isn't just one spot, it's a continuous, never-ending path. A guitar note isn't a single point in time. It's a wave of sound that changes from moment to moment. So how on earth could math, which we usually think of as being about static numbers, possibly capture something so alive?
The answer is it uses a totally different kind of math. This isn't the math of what is the final answer. No, this is the math of how is it behaving right now. It's a language that was built from the ground up to describe change itself. And that, my friends, is the world of differential equations.
Okay, so let's start with the basics. What exactly is an ordinary differential equation, or ODE as you'll hear it called?
The best way to think about this is to just forget everything you know about equations that give you a single number. An ODE is more like a recipe for behavior. It doesn't tell you where something is, it tells you the rules for how it's moving. That word derivative, that's just a fancy way of saying rate of change. So, an ODE is basically an equation that links a thing's position to its speed, and maybe its speed to its acceleration. It's literally a rule of motion.
And this, right here, this comparison is the absolute key. In algebra, we're like treasure hunters looking for a single number, right? X marks the spot, x equals 3. It's 1 point on a map. But with differential equations, we are finding the entire map itself. The solution isn't just a number, it's a whole function, a complete curve, a path that describes the behavior for all time. So for a rule like the rate of change is equal to the current amount, well, the solution to that is the famous exponential growth curve you see everywhere from biology to your bank account.
All right, so if this is a brand new language, where do we even begin? Well, we start with the simplest, most fundamental sentences. And in our world, these are the equations with what we call constant coefficients. Now I know, this might look a little intimidating, but let's break it down. Think of this as the ABCs of this new language. The y is just the position of something. The y with one little tick mark, mathematicians call that y prime, that's its velocity, its speed. And the y with two tick marks, yep, you guessed it, y double prime, that's its acceleration. The numbers, the 1 and the -6, they're just constants. All that means is that the rules for this system don't change over time. It's describing something simple, predictable, and in balance.
And this is where it gets totally amazing. These super simple forms, these basic mathematical sentences, are powerful enough to describe some of the most fundamental behaviors in the entire universe. We're talking about radioactive decay, population growth, the gentle swing of a pendulum, or even a guitar string slowly fading to silence. All of these completely different real-world things are written in the same simple language. But let's be real, the world is rarely that simple and clean, right? Things don't usually exist in a perfect little bubble, they get pushed around. So let's see how we can handle a bit of chaos. See that? Look at the right side of the equation. It's not 0 anymore. That extra stuff, that x squared plus 2x, represents some kind of outside influence. Maybe it's the wind pushing on a skyscraper, or a changing magnetic field messing with a circuit. The system is no longer in perfect, simple balance. Something external is pushing on it, making things way more complicated. So how in the world do you solve this mess? Well, the strategy is actually pretty logical when you think about it. First, you figure out how the system would behave naturally. You solve this simple balanced version where the right side is 0. Then, you figure out a piece of the solution that deals only with that external push. And finally, you just add them together. You combine the system's natural rhythm with the effect of the outside force. It's this beautiful 3-step process.
Okay, now we get to the really cool part, the boss level. What happens when the problems are so complex that our basic tools just don't cut it? Well, then we enter the realm of the legends. Equations so important, so iconic, they're named after the brilliant mathematicians who first cracked them.
First up, meet the Legendre equation. This beast was developed to solve some of the biggest problems in physics, like mapping out gravitational fields or figuring out how heat spreads through a sphere. And just look at it. The numbers in front of the y terms aren't just numbers anymore. They have an x in them. That means the rules of this system actually change depending on where you are. Way more complex. And here's the thing. The old methods completely failed here. The solution required a totally new technique. Finding the answer as an infinite string of terms, what's called a power series. But then something incredible happened. For certain special cases, certain energy levels,
These infinite, messy solutions simplified down into these beautiful, perfect little things called Legendre polynomials, and those became essential tools for all of modern physics.
Let's meet another legend, the Bessel equation. If you have ever seen the wild, beautiful patterns on the head of a vibrating drum or watched ripples spread out perfectly in a pond, you have seen a physical manifestation of this equation solution. It is the definitive language for describing things that happen in circles, in waves, in cylinders.
And then there's this one, the Hermite equation. This equation takes us into the truly bizarre and incredible world of quantum mechanics. It's absolutely fundamental to describing one of the most basic systems in all of quantum physics. This is the math that describes reality at its most tiny, most fundamental level. Just incredible.
So the big takeaway here isn't just that these were hard problems. It's that each one of these legendary equations, Legendre, Bessel, Hermite, and others you might have heard of like Chebyshev or Laguerre, they all force mathematicians and physicists to invent brand new ideas. The solutions they found, these special functions, became a whole new vocabulary for describing the physical world with a precision that was impossible before.
Okay, after that whirlwind tour, let's just zoom out for a second and think about the big picture. Why does this journey from simple rules to these legendary equations matter so much?
Well, look at the path we took. We started with a really basic question. How do we even talk about a world that's always in motion? We found the answer in the basics, those simple ODEs for predictable systems. Then we layered on some complexity to account for the messiness of the real world. And finally, we saw how tackling the absolute biggest challenges in science actually created a powerful, specialized new vocabulary for all of us to use.
And that really is what this is all about. It's not just scribbles on a page. It's about finding the underlying logic of the universe, the poetry and the motion of a planet, or the vibration of a single atom, and translating that beautiful logic into a language that we can understand, predict, and ultimately build with.
So the next time you see leaves swirling in the wind or watch a wave crash on the shore, just remember the language that's humming just beneath the surface. What are the rules that are governing that motion? What equation is writing the story of that exact moment? The world is just full of these incredible patterns, waiting for us to read them.